A single network glitch can trigger a cascade of duplicate entries in your downstream database. When a Kafka producer fails to receive an acknowledgement, it naturally retries, potentially appending the same data twice. This double write phenomenon breaks financial integrity and stateful computations. Standard at least once delivery is insufficient for mission-critical applications requiring strict consistency. To solve this, Kafka provides an idempotent producer that filters duplicates at the broker level. You activate this by setting the enable.idempotence configuration property to true in your producer settings. When idempotence is active, each producer instance is assigned a unique 64-bit producer identifier during initialization. Every message batch sent by this producer includes this identifier and a zero-based sequence number that increases with every record produced to a partition. The broker maintains a mapping of the last 5 sequence numbers successfully written for every producer identifier per partition. If a batch arrives with a sequence number that has already been committed, the broker silently drops the duplicate and sends an acknowledgement back. This mechanism ensures that even if the network fails during the acknowledgement phase, the retry will not result in a duplicate. The combination of the producer identifier and the sequence number provides a unique identity for every write request at the storage layer. Idempotence is limited to a single partition, but real-world workflows often span multiple topics and partitions. To achieve atomicity across different segments of the cluster, you must utilize Kafka transactions. Transactions allow a producer to write to multiple partitions, such that all succeed or none do.
To enable transactions, you must provide a unique string known as the transactional identifier in the producer configuration. This identifier persists across producer restarts and is the key to identifying a specific application instance in the transaction management system. When your application starts, it calls the initialize transactions method on the producer object. This step is mandatory and ensures that any previous transactions left in an ambiguous state by the same transactional identifier are properly closed or fenced off. The initialization process communicates with a component called the transaction coordinator, located on one of the brokers. The coordinator is responsible for managing the state of your transactions and ensuring the overall integrity of the atomic write process across the cluster. Once initialized, you start a logical unit of work using the begin transaction method. This marks the start of a period where all produced records are treated as a single atomic batch, regardless of which partition or topic they are intended for. As the producer sends data, it first registers each target partition with the transaction coordinator. The coordinator maintains a transaction log, which is actually an internal Kafka topic that records the state transitions of every active transaction in real time. When records are written to a partition during a transaction, they are stored in the log along with a transaction marker. These records are not immediately visible to consumers using the read committed isolation level until the transaction is officially finalized. If your application completes its processing successfully, it calls the commit transaction method. The producer sends a commit request to the transaction coordinator, which then updates the status in the transaction log to a prepared commit state.
The coordinator then writes a special commit marker to every partition involved in the transaction. These markers signify to consumers that the preceding records are now valid and safe to read, completing the atomic lifecycle of the data. In the event of an unrecoverable error, the application calls abort transaction. This prompts the coordinator to write abort markers across all partitions. These markers tell consumers to ignore the records associated with that specific transaction identifier and epoch. A common pattern in data engineering is the read-process-write cycle. Here, an application reads from one topic, processes the data, and writes the result to another topic while committing the source offsets as part of the same transaction. To link the consumer offsets to the transaction, use the send offsets to transaction method. This ensures that the offsets are only committed if the output records are successfully stored, preventing data loss or duplicate processing upon recovery. On the consumer side, the isolation level configuration determines visibility. By default, this is set to read uncommitted, which means the consumer sees every message as soon as it is appended to the log, even if the transaction fails. For Exactly-Once Semantics, you must set the isolation level to read committed. In this mode, the consumer fetcher will stop at the last stable offset, which is the offset of the first message belonging to an ongoing or open transaction. The last stable offset effectively acts as a high watermark for transactional data. Consumers will not see any records beyond this point until the corresponding transactions are either committed or aborted, ensuring a consistent view of the stream.
One major challenge in distributed systems is handling the zombie producer. This happens when a producer instance is partitioned from the network, A new instance starts, and then the original instance suddenly reappears and tries to write data. Kafka solves this using a producer epoch. Every time a producer initializes with a transactional identifier, the coordinator increments its epoch. Any requests from an older epoch are immediately rejected with a fencing error, preventing data corruption by stale processes. The transaction log is the source of truth. It is a compacted internal topic that tracks whether a transaction is ongoing, prepare commit, or complete. This ensures that even if a broker fails, another broker can take over the coordination. When a broker hosting the transaction coordinator crashes, the cluster elects a new leader for that transaction log partition. The new coordinator recovers the state of all active transactions from the log and resumes the commit or abort processes. The transaction markers themselves are invisible to standard applications. They are purely internal control messages used by the consumer fetcher to decide which data batches to deliver to the user space and which to discard. To minimize the overhead of transactions, Kafka batches the registration of partitions. This reduces the number of round trips between the producer and the transaction coordinator, keeping the latency impact of atomic writes relatively low for high-throughput systems. In a read-committed consumer, there is a slight increase in end-to-end latency. This delay is proportional to the transaction duration, as records are not visible until the commit marker is appended. Short transaction intervals are key for low latency.
The transaction timeout configuration is a safety net. If a producer does not heartbeat or finish a transaction within this period, the coordinator automatically aborts the transaction to prevent the last stable offset from being stuck indefinitely. Exactly-Once Semantics in Kafka streams is even simpler to implement. By setting the process when guarantee configuration to Exactly-Once version 2, the framework handles the complex transaction lifecycle, producer fencing, and state store consistency for you. Behind the scenes, Kafka Streams creates a separate transactional producer for every processing task. This isolation ensures that failures in one part of the topology do not affect the consistency or progress of other independent data streams. When using state stores with Exactly-Once processing, Kafka ensures that the state changelog and the output topic are updated atomically. If a task fails, the state is rolled back to the last committed checkpoint automatically. For high performance, the latest versions of Kafka use a feature called producer identifier snapshots. The broker periodically saves the state of sequence numbers to disk, allowing fast recovery without scanning the entire log during a restart. System analysts must monitor the transaction coordinator metrics carefully. High rates of aborted transactions often indicate application-level issues or overly aggressive timeouts that can degrade the performance of the entire cluster. Another critical metric is the age of the oldest open transaction. If a transaction remains open, it prevents the last stable offset from advancing, which causes read-committed consumers to lag behind and eventually stall. The transaction log itself requires careful tuning. The number of partitions in the transaction state topic should be high enough to distribute the coordination load across all brokers in a large-scale production environment.
Security is also integrated into the transactional model. You must ensure that the producer has the describe and write permissions on the transactional identifier to prevent unauthorized clients from interfering with or fencing legitimate producers. When designing your application, remember that Exactly-Once delivery is only guaranteed within the Kafka ecosystem. If your transaction involves an external database or service, you must use a distributed transaction or two-phase commit protocol. Wait times for consumers are also influenced by the commit interval. If you commit once every minute, consumers will experience a 1-minute delay. Balance your atomicity requirements with the desired freshness of your downstream data. Upgrading existing clusters to support Exactly-Once delivery requires no downtime. The brokers must be on version 0.11 or higher, and the transaction state topic must be created with the appropriate replication factors for high availability. Achieving total consistency in distributed systems was once considered a massive hurdle. With Kafka's transactional application programming interface, you can build resilient, stateful microservices that handle failures gracefully without ever processing the same message twice.